All right, welcome to The Explainer. Today, we're diving into some really cool research. We're talking about turning a common kitchen waste product, used cooking oil, into a valuable source of renewable energy. Yeah, you heard that right.
So let's get right into it. What if you could turn that old cooking oil into clean fuel just by using magnets? I know, it sounds like something straight out of a sci-fi movie, but this is the real deal. It's the core of a super powerful new way to make biodiesel, which is a much cleaner burning fuel. And to guide us through this, we're looking at a study co-authored by Dr. Mahmoud Karimi. Now, this is his area of expertise. He specializes in sustainable bioenergy and waste valorization, which is a fancy way of saying he figures out how to turn our trash into treasure. He's all about creating technologies for a circular bioeconomy. The work itself was published back in 2020 in the journal Renewable Energy, and it really gets to the heart of a huge challenge. How do we make biodiesel production not just possible, but actually cleaner, way more efficient, and truly sustainable for the long haul? Okay, so let's talk about the big picture. What's the problem this research is actually trying to solve? Let's set the stage for why this is so important. Well, look, biodiesel is a great renewable fuel, no doubt about it. But the traditional way of making it can involve some pretty harsh chemical catalysts. So this study explores a totally different route. They use enzymes, biological catalysts. It's a much gentler and way more environmentally friendly way of doing things. But of course, there's always a catch, right? Enzymes can be really expensive. So the big problem, the real nut to crack, is figuring out how to reuse them again and again and again, without them just, falling apart or losing their power. And that's exactly where this idea of immobilization comes into play. And this leads us right to the absolute core innovation of this entire study. They set out to build a biocatalyst that you can just grab with a magnet, so you can easily pull it out and reuse it for the next batch. Super clever. So here's what they did. The researchers took this specific enzyme, is called Burkholderia cepacia lipase. It's fantastic at breaking down fats, which is exactly what you need. And then they figured out a way to basically glue it or anchor it onto these teeny tiny magnetic particles. And how they actually built this thing is pretty brilliant. It's a four-step process. First, they start with a tiny iron oxide core. That's the magnetic part. Then they coat that with a layer of porous silica. Think of it like a spongy shell. After that, they activate the surface with a chemical linker. And finally, they attach the lipase enzymes to that linker. It's like building with Legos at the nanoscale. And the result? Well, you get a catalyst with a saturation magnetization of 45.69 amps squared per kilogram. Now, what that number really means is that it's super magnetic. It's strong enough so that when the reaction is over, you literally just use a magnet to pull the catalyst right out of the liquid. It's clean, it's simple, and it's ready for the next round. No messy or complicated filtering at all. Okay, so they've built this amazing new magnetic catalyst. But, having a great tool is only half the battle. You have to know how to use it, right? So the next big challenge was figuring out the absolute perfect recipe to squeeze out every last drop of biodiesel. Now, they didn't just guess. Instead of endless trial and error, the researchers used this really powerful statistical method called response surface methodology, or RSM. You can think of it like creating a 3D map to find the highest peak on a mountain. It helps you see how all the different variables work together to affect the final outcome, in this case, the biodiesel yield. And they systematically tested 4 key variables that they knew would be crucial. First, the amount of catalyst they added. Second, the reaction time, how long they let it cook. Third, the ratio of methanol to oil. And finally, of course, the temperature. All 4 of these had to be just right. So by plugging all that data into their model, they could create these incredible 3D surface plots. And these plots basically let them see the sweet spot. It's a visual way to find that peak, that absolute summit where all the conditions line up perfectly to give them the highest possible biodiesel yield. All right, so after all that super careful optimization and all that fancy statistical modeling, what was the result? What was the perfect formula they landed on? And the cool thing is, their model didn't just give them a ballpark estimate. No, it let them predict the exact recipe they needed to hit the absolute maximum output. And here it is, the perfect recipe. They found it required a catalyst concentration of 36% by weight of the oil. The reaction needed to run for 25 hours. The ideal methanol to oil molar ratio is 6.2, and get this, the best temperature was a pretty mild 34 degrees Celsius.
And when they put all those very specific optimized conditions together, the model predicted an absolutely incredible biodiesel yield, 92%. I mean, think about that. That's an amazing level of efficiency for converting waste into valuable fuel.
But listen, a high yield is awesome, but it's really only half the story. For this whole thing to be truly sustainable and, affordable, that magnetic catalyst had to be reusable. That was the whole point, right? And, well, here's the proof in the pudding. They tested it. When they recovered the catalyst and used it again, it kept on working. The first cycle gave them a 74% yield. The second cycle, still a really good 71%. And even on the third go-around, it produced a solid 66% yield. What this shows us is that the immobilized enzyme, this magnetic biocatalyst, is incredibly robust. It's stable. After 3 uses, it only lost about 11% of its activity, and that reusability is what makes this whole process potentially viable on an economic industrial scale. So what's the big takeaway here? At the end of the day, this research is just a fantastic proof of concept. It's such an elegant solution, combining cutting-edge nanotechnology with biochemistry to solve a really practical, real-world problem: what to do with our waste and how to generate clean energy. And it really makes you think, doesn't it? I mean, if we can turn old fryer grease into clean fuel with a bunch of tiny magnets, what other hidden resources are just sitting there waiting to be unlocked by the next smart, reusable catalyst? What other transformations are just one clever idea away?